I want you to just try and picture a scenario for a second. You are driving down the highway, the weather is completely clear, the road is open, and you're cruising right at, let's say, 70 miles per hour in your brand new electric vehicle.
Right, just a totally normal drive.
Exactly. Everything feels incredibly smooth. There is, barely any noise at all, just the faint hum of the tires on the pavement.
Mm-hmm.
You were sitting inside this 2-ton cage made of high-strength steel and aluminum, and you're being propelled forward entirely by invisible electromagnetic forces.
Which is amazing when you think about it.
It really is. But then, and this is the scenario, in a fraction of a single millisecond, the internal components of your EV's drive motor just physically lock up solid.
And I'll jump in right there because, well, that is exactly where the peaceful drive ends.
Yeah, I imagine so.
The kinetic energy of a 2-ton vehicle traveling at 70 miles per hour is just massive. I mean, it's astronomical. When a motor locks up instantly at those speeds, you aren't just dealing with a broken part. You are dealing with absolute mechanical and electrical violence.
Yeah.
In the, the sterile environment of an engineering lab, we'd call this a motor stall or a shaft-locked event.
A shaft-locked event.
Yeah, but out on the highway, it is basically a worst-case scenario.
And that is exactly the nightmare that we are dissecting today on this deep dive. Because if the wheels just lock, does the car violently spin out of control?
Right.
Or, does all that electrical energy suddenly have nowhere to go and the battery just catches fire right there on the asphalt?
That's the fear, right?
Exactly. Or, and this is what we're going to get into, is there some microscopic, invisible safety net operating underneath all of it that, catches you before you even realize you are falling?
Well, spoiler alert, there is a safety net.
Mm.
But the mechanism of how that net actually functions, how it detects the failure, isolates it, and saves the vehicle in literally a matter of milliseconds, is arguably one of the most complex, high-stakes engineering feats in modern transportation.
It's just wild. And to understand it, we've got our hands on this ultra-high-level, deeply technical diagnostic engineering specification.
Yeah, it's very dense stuff.
Super dense. It is essentially a forensic analysis of an automotive fault mode that they designate as A07. Now, this falls under the ASIL D category.
Right, ASIL D.
For those of you who follow automotive engineering, you probably know what that means, but let's establish the gravity here for everyone. ASIL D is like the absolute highest severity level in automotive functional safety, correct?
It is the absolute ceiling. I mean, ASIL stands for Automotive Safety Integrity Level.
Okay.
When an engineering team labels a fault mode as ASIL D, they are explicitly stating that if this system fails, the risk of a fatal accident or a catastrophic injury is just unacceptable.
Unacceptable, meaning they have to engineer it so it practically never happens.
Exactly. The acceptable failure rate for an ASIL D component is essentially 10 to the power of -8 per hour of operation.
Wow.
Which is practically zero. This isn't, a faulty check engine light or a little glitch in your infotainment screen.
Right, your Bluetooth dropping out.
Yeah, exactly. This is literal life or death logic.
So our mission for this deep dive is to trace the entire life cycle of this fatal A7 motor stall. We aren't just going to look at the crash itself. We are actually going backwards.
It's the only way to really understand it.
Right. We want to understand the...
Right. It forces us to translate these hardcore engineering concepts, things like field-oriented control algorithms and the quantum-level physics of silicon carbide, switching into the actual, tangible, mechanical survival of the car you drive every single day.
So let's start right at the beginning, the failure itself. Because before we can really appreciate how the computer saves the car, we have to understand the anatomy of a stall.
How it breaks.
Yeah. How does a highly advanced liquid-cooled EV motor simply freeze? The source material outlines 4 primary root causes. And I'm looking at the first one here, and I'll be honest, it sounds almost like science fiction.
Oh, I know which one you're looking at.
It's this phenomenon called bearing seizure via EDM.
Electrical discharge machining.
Right.
And what makes this first cause so terrifying is that it's almost entirely invisible right up until the very moment of catastrophic failure.
Invisible.
Yeah, completely. And it all stems from what is otherwise a massive leap in EV technology. I'm talking about the adoption of silicon carbide or SIFT MOSFETs in the power inverters.
Okay, I know silicon carbide is sort of the gold standard for EV efficiency right now because, well, it lets cars charge faster and drive further.
Exactly. It's brilliant for efficiency.
But how does a completely digital efficiency upgrade cause a physical heavy metal motor bearing to just lock up?
Well, it all comes down to the speed of the electrical switching. An inverter's main job is to take the direct current, the DC power coming from the battery, and essentially chop it up,
Right, switching it on and off.
right, thousands of times a second
Phew.
to create the alternating current, the AC, that actually spins the motor.
Oh.
Now, traditional silicon chips were fast, but these new silicon carbide chips are violently fast.
Violently fast. I like that phrasing.
It's accurate. They create these extreme voltage changes, switching at rates of 10 kilovolts per microsecond or sometimes even more.
Wait, hold on. 10 kilovolts per microsecond? You're saying 10,000 volts are shifting in 1/millionth of a second?
Yes, the slope of that voltage change, what engineers call the dV/dt, is incredibly steep. Now, in physics, anytime you have two conductive materials that are separated by an insulator, what do you have? You have a capacitor.
Right, basic electronics.
Well, inside an EV motor, you have the stationary stator coils carrying this high voltage AC, you have the physical air gap in the motor, and you have the spinning metal rotor.
Okay, so the metal, the air, the metal.
Exactly. That physical arrangement accidentally acts like a giant unintended capacitor.
So the motor is basically tricking itself into storing electrical energy where it definitely shouldn't be.
Precisely. Because those silicon carbide switches operate so incredibly fast, that high dV/dt induces a high frequency, what they call a common mode shaft voltage.
A common mode shaft voltage.
Right. It's essentially a rogue electrical charge, usually sitting somewhere between 70 to 370 volts, and it literally just builds up physically on the spinning metal shaft of the rotor.
But the shaft is just a giant piece of metal. I mean, that electricity has to find a path back to the ground eventually, right?
It does. It desperately wants to get to the grounded outer casing of the motor. And the only physical bridge between that spinning shaft and the stationary grounded casing,
Wait, don't tell me.
it's the metal bearings that the shaft actually rests on.
Oh, wow.
Yeah. Now, inside those bearings, there's this microscopic film of lubricating oil. And oil, as you know, is an insulator.
Right, it resists electricity.
Exactly. But as that 370 volt builds up on the shaft, it pushes harder and harder against that tiny oil film
Until the oil just can't hold it back anymore.
until the voltage literally exceeds the dielectric strength of the oil. And when that finally happens, the electricity arcs right through the oil.
Like a literal lightning strike.
It is a microscopic, high-energy plasma discharge, a tiny lightning strike happening inside the bearing. But the terrifying part is, it isn't just one strike.
Because it's switching thousands of times a second.
Exactly. Because the inverter is switching thousands of times a second, this lightning storm is continuous. This is the electrical discharge machining part.
The EDM.
Right. Every single microscopic lightning strike blasts a tiny, tiny crater into the hardened steel of the bearing. Over thousands of miles of driving, this plasma cutter effect creates this washboard pattern on the metal, and effect engineers call fluting.
So this invisible lightning is literally machining away the hardened steel while you're just commuting to work.
Yes, and it gets so much worse. The intense localized heat of the plasma actually burns the lubricating grease.
Oh, man.
It turns it into solid carbon, and it melts the delicate metal cages that keep the individual ball bearings evenly spaced out.
So you have no grease and ruined metal.
Exactly. Without grease and with cratered surfaces, the friction just skyrockets. The bearing heats up, expands, and eventually destroys itself completely. It seizes solid.
Mechanical lockup at 70 miles per hour, caused entirely by invisible electrical arcs.
Invisible electrical arc.
That is deeply, deeply unsettling. But the document also outlines a second root cause. And this one sounds far less elegant and much more brutally physical. It's called rotor seizure, or sweeping.
Yeah, if the first cause was a microscopic electrical storm, this one is just a sledgehammer.
A sledgehammer, let's hear it.
So an EV motor consists of that heavy metal rotor spinning inside the stationary stator. The physical air gap between the spinning part and the stationary part is incredibly small.
Why so small?
To maximize magnetic efficiency, you want them as close as possible without touching. So we are talking about microscopic manufacturing tolerances here.
Right. The specification mentions a tolerance called TIR, total indicator reading, and it says it absolutely cannot exceed 0.05 millimeters.
That measurement is absolutely critical. TIR is essentially a measurement of how far off-center the rotor is spinning, how much it wobbles.
Okay, wobble is bad.
Very bad. Now, to put 0.05 millimeters in perspective, you might just think of it as roughly the thickness of a human hair. But let's look at it through the lens of thermodynamics.
Okay, lay the thermodynamics on me. Why is a human hair of wobble the magic number?
Because metal is not static. When a motor is sitting in the factory at room temperature, It might measure perfectly centered. But when you are out there pushing a car up a mountain, the internal temperature of that motor might hit 120, maybe even 150 degrees Celsius.
That's incredibly hot.
It is. And at those temperatures, the metal of the rotor physically expands outward. And at the exact same time, it's spinning at 10,000 to 15,000 RPM, so immense centrifugal forces are actively trying to stretch the metal outward too.
Wait, so the rotor is literally growing larger and getting closer to the stator wall as you drive.
Exactly. The air gap physically shrinks. Now, if there is a slight manufacturing error, say the layers of laminated steel on the rotor stack up just slightly crooked, the center of mass is thrown off.
Right, yeah.
The rotor starts to vibrate. If the speed of the motor hits a resonant frequency, those vibrations amplify wildly. So now you have a heavy, hot, expanding piece of metal wobbling at 1,000 hertz.
And it just eats up whatever is left of that tiny little air gap.
It physically scrapes against the inside of the stator. It sweeps the inner wall. And the moment that spinning rotor touches the stationary stator, the friction is unimaginable.
It just catches.
It bites down into the copper coil windings, snapping them instantly, and you have a violent, catastrophic mechanical seizure.
Sledgehammer is definitely the right word for that.
Oh, yeah.
But let's look at the third cause, because I read this one and it completely messes with my head. The text calls it an electromagnetic pull-out stall.
Ah, yes.
And based on my reading, there is absolutely nothing physically broken in this scenario. Like, the bearings are pristine, the rotor is perfectly balanced, the air gap is totally fine, the physical machine is perfect, but it still stalls. How does that even happen?
Right. This is a failure of pure mathematics.
Mathematics.
Yeah. To understand this, we have to look at how modern EV motors are controlled. They don't just rely on dumping raw electricity into coils like an old RC car. They use an incredibly complex algorithm called field-oriented control, or FOC.
Okay, I've seen that term, FOC. What does it actually do in simple terms?
So an AC motor relies on a rotating magnetic field in the stationary stator, and that field pulls along the permanent magnets on the spinning rotor.
Okay.
To get maximum torque, which is maximum pushing power, the magnetic field of the stator must be kept exactly 90 degrees ahead of the magnetic field of the rotor at all times.
It's like, okay, like dangling a carrot perfectly out of reach of a horse. If the carrot is too close, the horse stops pulling. If it's too far, the horse just gives up. It has to be exactly 90 degrees ahead.
That is a great way to visualize it. But to keep that carrot exactly 90 degrees ahead, the car's computer has to know the exact microscopic angle of the spinning rotor at any given microsecond.
It has to know exactly where the horse's head is.
Exactly. It uses complex math things like Clark and Park transformations to calculate the exact current vector required to maintain that perfect 90-degree push.
So what breaks? If the hardware is fine, what goes wrong?
The angle estimation. Let's say a calibration step was skipped at the factory. Or, more commonly, let's say you just floor the accelerator pedal to pass a truck on the highway.
You demand a ton of power.
Right, massive acceleration. That extreme surge of current can actually cause the magnetic steel in the motor to become deeply saturated. The magnetic fields distort, and the sensors get confused. The text states that if the computer's estimation of the rotor's angle gets delayed by more than just 15 degrees, the entire FOC mathematical matrix completely collapses.
The computer just loses track of the rotor?
Completely. The computer thinks the rotor's in one position, but physically, the rotor has moved past it. So the stator fires its magnetic push at the completely wrong time.
Oh, no.
Instead of pushing the rotor forward, the magnetic fields clash. The torque plummets instantly to zero. Then, as the rotor continues to spin past the misaligned fields, the stator actually pushes backward against the rotation.
Yeah.
You get violently alternating positive and negative torque.
It's like, okay, imagine you have two trapeze artists. It's all about timing and physics, right? The catcher swings, the flyer lets go. They expect to meet in the exact same space at the exact same millisecond.
Right.
But suddenly, one of them miscalculates their swing by just a tiny fraction of a second. The physical bodies are perfectly fine, their muscles work, but the math of the timing is completely shattered. Instead of a smooth catch, they just violently collide in midair. The math fails, and the physical system crashes.
That is exactly it. The physical motor is doing exactly what the computer tells it to do, but the computer is telling it to tear itself apart.
Which brings us to the fourth and final root cause in our anatomy of a stall, and this is external lockup and thermal meltdown.
This scenario is a little different, right? Because the failure doesn't start inside the motor itself.
Right, exactly. This is an external trauma. Imagine a scenario where a massive piece of road debris kicks up and physically jams the wheel, or, the internal gears in the transmission shatter and lock the drivetrain solid. The motor is physically forced to 0 RPM.
But the driver is panicking and still has their foot on the accelerator? Or maybe the cruise control is still trying to maintain 70 miles per hour? Exactly. The system doesn't immediately know the wheel is jammed. It just knows the car is slowing down when it shouldn't be, so it demands a massive torque to try and overcome the resistance.
It fights back.
It blasts maximum DC current from the battery into the stator coils, trying desperately to force the motor to turn.
But if the motor can't turn, where does all that electrical energy actually go?
It has nowhere to go but into heat. And here is where we really need to look at Ohm's law and something called back electromotive force, or back EMF.
Break that down for me. Why does a stalled motor heat up so much faster than a motor that's just spinning normally?
Well, when a normal motor is spinning, the magnets moving past the copper coils actually generate their own voltage that pushes backward against the battery. That is the back EMF.
Okay, so it pushes back.
Right. This natural backward push acts as a massive resistor, limiting how much current can actually flow into the motor from the battery.
So it basically regulates itself just by spinning.
Yes. But when the motor is externally jammed at 0 RPM, there is 0 rotation, which means there's 0 back EMF.
The natural resistance is just gone.
Gone. The only thing limiting the raw power of the battery is the tiny physical resistance of the copper wire itself. The current just spikes to catastrophic levels, pulling thousands of amps.
And because the motor isn't spinning, I'd imagine the internal cooling fans or the liquid coolant pumps might not be circulating effectively either.
Exactly. You lose cooling right when you need it most. The localized heat builds up exponentially. This is joule heating, which is a function of current squared multiplied by resistance, or I squared R.
Okay.
Because the heat scales with the square of the current, a massive current spike creates an unfathomable amount of heat. Within mere seconds, the copper coils get so hot, they literally melt right through their protective polymer insulation.
So the bare wires touch each other, causing massive internal short circuits.
And you have a complete thermal runaway. The motor is basically incinerated from the inside out.
Okay, so we've established the violence here. We have EDM lightning eating the bearings, 10,000 RPM scraping, shattered mathematics, and external thermal meltdowns. So here is the million-dollar question.
Let's hear it.
If an external jam can melt the motor in a matter of seconds and a rotor sweep can snap wires instantly, how fast does the car's computer actually have to react to save the vehicle and the driver?
The ASIL D safety specification gives us a hard number on this. The system has a fault-tolerant time interval, an FTTI, of strictly 60 milliseconds or less.
60 milliseconds. I really want to pause on that number. The average human blink takes about 300 milliseconds.
Right.
You are telling me the car has to detect a catastrophic failure, verify that it's real, and execute a survival strategy in 1/5 of the time it takes a human being to blink their eyes.
It is functionally instantaneous. And this brings us to the second massive phase of this specification, the technical architecture and software-hardware co-diagnostics. How does the 60 millisecond brain actually work?
Yeah, let's get into it. How does a computer know it is dying faster than a blink? The text outlines this multi-layered defense system, starting with something called the Dewar checker system and PI saturation.
Right. So to achieve ASIL D certification, a single microprocessor core is legally not enough. You must have hardware redundancy. The main computer brain has one highly powerful core, the Dewar, that runs all the complex FOC math and actively tries to spin the motor.
Okay, the Dewar does the work.
Right. But right next to it is a secondary core, the checker.
And the checker's only job is to just sit there, watch the Dewar, and make sure it hasn't gone completely insane.
Precisely. The checker is highly skeptical. It specifically monitors the PI, or proportional integral controller. The PI controller is basically the digital gas pedal.
Okay.
When the motor starts to lock up, the speed obviously drops. The Dewar sees the speed dropping, so it reacts by pushing the PI controller to a 100% saturating limit.
Yeah.
It demands maximum voltage to try and force the motor to spin.
It just floors the pedal.
Yes. The checker watches this happen. It constantly compares the massive electrical power being pushed into the motor against the physical speed of the rotor. If the checker sees that the Dewar is demanding 100% maximum power for just 1.5 milliseconds, but the motor speed is reading absolute zero, the checker immediately throws a red flag. It triggers the stall protocol.
Hold on, why wait 1.5 milliseconds? If the pedal is floored and the speed is zero, why doesn't the checker kill the power at like 0.1 milliseconds. Why wait at all?
Because the real world is noisy. If you hit a massive pothole, the sudden shock can cause a microscopic, instantaneous spike in the sensor readings. If the system reacted instantly to every tiny spike, your car would shut down on the highway every time you hit a bump.
Oh, that makes sense.
Yeah, the 1.5 milliseconds acts as a debounce timer. It is just long enough to filter out the random electrical noise and confirm that the extreme power demand is real and sustained, but it's still short enough to fall safely within that 60 millisecond survival window.
Okay, I follow the logic. But here is my major concern with this. What if the motor is actually spinning perfectly fine at 70 miles per hour, but the tiny speed sensor chip inside the motor just breaks, right? If the chip dies and reads 0, the checker sees 0 speed, sees high power demand, and thinks the motor is stalled. You really do not want the car slamming into an emergency shutdown on the highway just because a $5 sensor failed.
That is the single most critical challenge in automotive diagnostics.
Yeah.
Avoiding false positives. And that is exactly why the second layer of defense is the multi-source plausibility check.
The lie detector.
Exactly. The car does not trust any single sensor. It acts as a continuous lie detector test, constantly cross-referencing 3 completely independent data streams.
Walk me through these 3 streams.
Sure. Data stream number 1 is exactly what you mentioned. The physical speed sensor chip, it's usually an RDC, a resolver to digital converter, bolted right onto the motor shaft itself. It provides the hard physical data.
Okay, so stream 1 is the physical hardware. What is stream 2?
Stream 2 is entirely virtual. The software runs an incredibly complex background algorithm known as a sensorless observer. It often uses high-frequency injection or sliding mode observer math.
Virtual. How does it measure speed without a sensor?
Instead of looking at a physical sensor, this algorithm analyzes the electrical blowback, the back EMF voltage and current ripples we talked about earlier, coming back up the high-voltage cables from the coils. By analyzing the shape of the electricity itself, it mathematically deduces how fast the motor must be spinning.
That is wild. It basically feels the electrical resistance to guess the physical speed.
Exactly.
And stream number 3.
Stream 3 comes from entirely outside the motor subsystem. The main computer reaches out over the car's CAN bus network and talks to the ESP or ABS system, the anti-lock brakes.
Right.
It asks the wheel speed sensors, hey, how fast are the physical tires rolling on the pavement?
So we have the motor's physical sensor, the motor's electrical shadow, and the actual tires on the road.
Exactly. Now the logic matrix kicks in. If the physical RDC chip suddenly says 0 RPM, but the virtual sensorless observer feels a massive back EMF voltage indicating 10,000 RPM, and the ABS system confirms the wheels are rolling at 70 miles per hour.
The computer knows the RDC chip is just lying. It's a fake stall. The hardware sensor just broke.
Yes. The computer logs a sensor fault, it switches over to driving the motor entirely using the virtual sensor math, and safely limps the car to the side of the road. No panic shutdown.
But what if all 3 data streams align? What if the physical chip reads 0, the virtual electrical shadow disappears and reads 0, and the ABS wheel sensors violently decelerate to 0, all while the doer is demanding maximum power?
Then there's absolutely no doubt. The computer confirms the absolute worst-case scenario. It is a genuine, catastrophic physical lockup. The lie detector has confirmed a fatal event. And once that is confirmed, the 60-millisecond brain enters its most desperate phase, the split-second decision. They call it the symmetric fallback.
The car basically has to save itself. And the specification divides this emergency response based on how fast the car is currently moving. Let's start with low speed.
Okay.
You are crawling in stop-and-go traffic, say 5 miles per hour, and the gearbox just shatters, the motor jams. What is the survival strategy there?
At low speeds, the kinetic energy of the car is negligible. The primary immediate danger is that I²R thermal meltdown we talked about earlier, the localized heat spike. So the system executes a strategy called active open circuit, or AOC. It is also commonly known as freewheeling.
Freewheeling, it just turns off the switches. It just cuts the power from the battery to the motor.
Instantly. It opens all the MOSFET gates, physically isolating the battery from the motor coils. It kills the electrical current dead in its tracks. Without current, the joule heating stops immediately, and the motor is saved from melting down.
Now, I have to push back here for a second. Why is turning the motor completely off a good idea? If I'm driving, even at low speeds, and the car suddenly loses all propulsion power, doesn't that create an entirely new safety hazard? You just turned a drivable vehicle into a heavy, unpowered brick in the middle of traffic.
That is a very valid point, and honestly, it's a constant debate in safety engineering. But
Oh.
you have to weigh the hazards against each other. An unpowered vehicle coasting to a stop in low-speed traffic is a hazard, yes.
Yeah.
But a vehicle that actively catches fire and incinerates the occupants because the high-voltage cables melted together.
Yeah, that's worse.
Right, it's a catastrophic, non-survivable hazard. Automotive safety standards always prioritize preventing thermal events fires over maintaining drivability during a critical fault.
Okay, I concede the point. Fire is definitely worse than coasting. But that is at 5 miles per hour. Let's go back to our highway scenario. 70 miles per hour. The motor locks up, or maybe the math fails and it starts tearing itself apart. If turning the power off is the solution at low speed, why can't the computer just execute that same active open circuit at high speed? Just pull the plug.
Because if you execute a simple active open circuit at 70 miles per hour, you don't just lose power, you create a high-voltage bomb.
Okay, you need to explain the physics of that. Why is cutting the power at high speed suddenly a bomb?
To understand this, we really have to look at Faraday's law of induction. An electric EV motor isn't just a motor. It is fundamentally identical to a high-powered generator. You have a massive, heavy rotor packed with incredibly powerful permanent magnets. And at 70 miles per hour, that rotor is spinning at roughly 10,000 to 12,000 RPM inside the copper stator coils.
Right, and moving a magnet past a coil of wire generates electricity.
Exactly. When the car is operating normally, the battery voltage is actively pushing against the motor. But if you suddenly cut the connection, if you trigger an active open circuit, the battery obviously stops pushing. However, that heavy rotor doesn't just stop instantly.
It has momentum.
It has immense kinetic energy. It keeps spinning at 12,000 RPM.
So it instantly turns into a generator.
It becomes what we call an uncontrolled generator, or UCG.
Hmm.
And because the generated voltage is directly proportional to the speed of the spinning magnets, at 12,000 RPM, it generates a massive wave of electricity. This back EMF voltage can easily spike far higher than the maximum voltage of the car's own battery.
And since you've cut the connection, that massive wave of voltage has literally nowhere to go.
It has nowhere to go but backward. The electricity slams into the freewheeling diodes inside the silicon inverter. If the generated voltage exceeds the physical breakdown limits of those electrical components, it punches right through them. It violently overcharges the DC link capacitor, which will explode, and then that extreme overvoltage continues backward into the battery pack, potentially causing a catastrophic high-voltage fire.
Wow.
You simply cannot just drop a wall in front of that much generated energy. You have to bleed it off safely.
Okay, so if cutting the power blows up the electronics and leaving the power on melts the motor, what does the 60-millisecond brain actually do at 70 miles per hour?
It executes a highly choreographed two-stage maneuver called a stepwise active short circuit, or ASC.
Wait, active short circuit. You are telling me the safety mechanism is to intentionally short circuit the high voltage system. That sounds like the absolute last thing you would ever want to do.
I know it sounds completely counterintuitive, but you aren't short-circuiting the battery itself. You are short-circuiting the motor coils onto themselves, isolating the battery entirely. And it must be done in two exact stages to prevent snapping the physical drive shaft.
Okay, walk me through the stepwise process.
So phase one. The system intentionally turns on just two of the three electrical phases in the lower half of the inverter. It creates an asymmetrical short circuit.
Why only two phases?
If you instantly short-circuit all three phases of a motor that's spinning at 12,000 RPM, the opposing electromagnetic force is so violently powerful that it acts like slamming a steel rod into the spokes of a bicycle wheel.
Ouch.
The transient torque spike is so massive it can physically snap the hardened steel drive shaft in half, sending metal shrapnel straight into the gearbox. By only shorting two phases initially, you absorb the initial violent shock wave of the magnetic energy. It basically takes the sharp edge off the transient torque.
So phase one softens the blow. Then what?
The computer waits exactly 1.5 milliseconds, just long enough for that initial violent mechanical spike to pass. Then, phase two kicks in. The computer triggers a complete symmetrical short circuit across all three lower gates of the inverter.
It closes the loop entirely.
Yes, it creates a closed loop entirely within the massive copper coils of the motor. The uncontrolled generator is still generating electricity, but instead of that voltage blasting backward into the delicate electronics, the electrical current simply loops round and round within the thick copper stator coils.
It forces the motor to basically swallow its own poison.
That is a brilliant way to phrase it. The heavy copper coils have enough thermal mass to safely absorb that energy. By trapping the current in this short-circuit loop, the system physically clamps the deadly voltage spike to a safe limit, usually 720 volts or less. Furthermore, the motor's own internal inductance acts to naturally limit the short circuit current.
So the magnetic drag of the short circuit basically turns the motor into a massive electromagnetic brake, safely dissipating the kinetic energy of the car into thermal heat inside the metal block rather than blowing up the battery.
Exactly. And the most staggering part is that all of this logic, the PI saturation check, the triple redundant plausibility matrix, the decision to use ASC instead of AOC, the two-stage asymmetrical to symmetrical braking, all of it is calculated and executed by the microprocessors in under 60 milliseconds.
It is utterly exhausting just trying to conceptualize the sheer volume of mathematics happening under the hood while you were simply changing lanes on the highway.
It is an incredible achievement in software engineering.
Mhm.
But if we connect this to the bigger picture of vehicle safety, there is a fundamental glaring vulnerability with everything we just spent the last 20 minutes discussing.
I knew there was a catch. What is the vulnerability?
Yeah. Software. Software is brilliant, software is adaptable, but software is bound by the laws of computing. It takes time to process. It has to read analog voltages, convert them to digital signals, run the FOC math, check logic gates, and send out a command. And more importantly, software can crash.
Right.
Microprocessors can experience buffer overflows or get confused by intense electromagnetic interference.
So you're saying that if the microprocessor is overwhelmed or blinded during that critical 60 millisecond window, the car dies. The software brain just isn't enough.
It absolutely is not enough for an ASIL D rating. You cannot rely solely on code. You need a backup that exists in the physical realm. And this brings us to the third part of the specification, DFMEA, which stands for Design Failure Mode and Effects Analysis.
Okay.
This section is entirely about how engineers design the physical hardware blueprints so that the car actively resists these failures from ever happening or handles them purely through hardware without ever asking the software for permission.
Bulletproofing the blueprint. Let's look at the first physical defense. The specification calls it hardware bypassing the software, specifically through gate over voltage protection, or OVP.
This is one of the most elegant solutions in modern electrical engineering. First, the design rules mandate the use of ultra-isolated driver chips with a common mode transient immunity, or CMTI, of greater than 100 kilovolts per microsecond.
So they are heavily physically shielded against that high-frequency electrical noise we talked about earlier.
Yes, but the true genius lies in a dedicated, purely physical analog hardware circuit built directly into the inverter itself. It incorporates an active Miller clamp and a gate over voltage protection loop.
Okay, break that down for me. If the software's too slow, how does a dumb hardware circuit protect the car from a massive voltage spike?
Let's go back to our high-speed lockup scenario, the motor jams. The massive uncontrolled generator voltage surge starts rushing back toward the inverter. Normally, the software brain has to see this voltage rise on a sensor, process the math, and trigger the emergency short circuit. But this hardware circuit acts as a physical tripwire. It uses analog comparators that constantly measure the raw voltage.
It doesn't process data, it just reacts to physical pressure.
Exactly. If the hardware comparator detects that the voltage surge is crossing a specific critical threshold, it doesn't send a warning to the main processor. It completely bypasses the software entirely. The hardware circuit physically forces the emergency short circuit, the ASC on its own, in under 100 microseconds.
Wait, microseconds. Earlier we were talking about a 60 millisecond window.
Yes. Well, 100 microseconds is 1/10 of a single millisecond. It is hundreds of times faster than the software limit. The analog hardware throws the emergency electromagnetic brakes before the software brain even realizes there is a problem. It reacts instantly to prevent the delicate silicon microchips from suffering electrical overstress, or EOS.
It is exactly like a human spinal reflex. Think about it. If you accidentally place your hand on a red-hot stove, you don't actually think about moving your hand.
Right, you just flinch.
Yeah, the pain signal travels from your hand, hits your spinal cord, and your spinal cord immediately sends a physical command back to your muscles to pull your hand away. That physical reaction happens instantly. The pain signal hasn't even reached your conscious brain yet. The hardware reflex protects the body while the slow conscious brain is still figuring out what just happened.
That is a phenomenal analogy. The hardware reflex acts to save the vehicle's electrical system, buying the software brain the time it needs to wake up, assess the fault, and take over long-term control.
Okay, so hardware reflexes handle the voltage spikes. But what about the ghostly lockup we talked about earlier? The electromagnetic stall or the FOC math fails because the magnetic fields saturate and the car just loses track of the rotor's angle. How do you fix a complex mathematical error with a physical blueprint?
You give the system a compass that simply cannot be corrupted. The specification mandates the inclusion of search coils. This is a form of algorithmic redundancy built right into the physical copper and steel of the motor. Engineers literally designed the blueprints to include tiny redundant wire coils hidden deep inside the stator slots.
Hidden coils, like secret backup sensors woven into the main motor.
Exactly. And the brilliance of these search coils is that they have absolutely zero physical or electrical connection to the main high-voltage power cables. They do not carry the massive driving current. Because they are physically and electrically isolated, they are completely immune to the extreme temperature drift or the deep magnetic saturation that blinds and confuses the main software algorithms.
They just sit there quietly, watching the magnetic field spin by.
They act as a pure physical backup compass. Even in the middle of a chaotic high-power electromagnetic stall, where the main sensors are feeding garbage data to the computer, these isolated search coils can independently track the exact angle of the rotor by measuring tiny induced voltages. They feed that undeniable physical truth back to the system, allowing the FOC math to resynchronize and recover the motor.
It is like navigating a ship by the stars when your GPS system goes down. The stars aren't affected by cell towers crashing or software bugs. They are a physical constant.
Precisely. And the final major piece of the DFMEA blueprint defense goes all the way back to our very first root cause, the invisible EDM lightning destroying the bearings.
Yeah.
How do you defeat a microscopic electrical storm?
Well, if it's lightning, you build a lightning rod.
You build a microscopic lightning rod. The blueprints legally mandate the installation of high-conductivity carbon brush, shaft grounding rings, or in some high-end applications, the use of hybrid ceramic bearings.
Let's talk about the grounding rings first. How do they work?
Remember that the parasitic capacitance causes a high voltage to build up on the spinning shaft, and it desperately wants to arc through the oil in the bearing to reach the ground. The carbon grounding rings wrap around the shaft. Carbon is highly conductive. It creates a physical bridge with a path of extreme low resistance.
So instead of the electricity building up pressure and exploding through the insulating oil film, it just takes the easy path through the carbon brushes straight to the grounded metal casing.
Exactly. It completely neutralizes the voltage buildup. No voltage pressure means no arcing. No arcing means no micropits, no fluting, and the steel bearing survives the life of the car. Alternatively, they use hybrid ceramic bearings. The ball bearings themselves are made of non-conductive ceramic material instead of steel.
Which is an insulator.
Right, ceramic is an absolute insulator. It completely severs the capacitive circuit. The electricity physically cannot cross the gap, eliminating the EDM threat entirely.
And I'm looking at the blueprints for the rotor sweeping issue too. It explicitly mandates that the manufacturing tolerance for rotor wobble, that TI argument, must absolutely be maintained under 0.05 millimeters, even accounting for thermal expansion at maximum operating temperatures.
Right. It eliminates the mechanical scraping failure mode by mathematical design.
It really illustrates the concept of defense in depth. You have this intricate web where physical hardware and digital software are intimately woven together, constantly covering each other's blind spots. But I have to play the skeptic again here.
Go for it.
All of this is just ink on paper. A perfect, bulletproof CAD blueprint means absolutely nothing if the guy working on the assembly line on a Friday afternoon is tired and skips a step.
And that is the transition from theoretical engineering to physical reality. How do automotive plants ensure these microscopic tolerances and hardware fail-safes are actually built flawlessly millions of times over on a noisy, fast-paced assembly line?
Which brings us to Section 4. PFMEA, Process Failure Mode and Effects Analysis, the factory controls. Because frankly, you cannot rely on human feel or visual inspection when you are dealing with a 0.05 millimeter tolerance. A human eye cannot see that.
You absolutely cannot rely on humans for this level of precision. In fact, the overarching philosophy in the PFMEA specification is about entirely removing the human element from the critical physical assembly steps. Take the installation of those delicate motor bearings we just talked about. The process specification explicitly bans the hammer.
Banning the hammer, meaning no manual force whatsoever.
None. In a traditional shop, a mechanic might tap a bearing into a casing using a rubber mallet and a brass drift. If it feels straight, it is good enough. But in an ASIL D EV factory, that is illegal. A human tapping a bearing will inevitably introduce a microscopic misalignment.
But if it's microscopic, who cares? If it goes in the hole, isn't it fine?
No, because a misaligned bearing introduces internal preload stress. It might spin perfectly fine on day one, but that uneven stress will cause the metal to fatigue prematurely, and the bearing will shatter violently at 70 miles per hour when the car has 30,000 miles on it. To prevent this, factories use automated concentric servo presses. But these aren't just dumb hydraulic rams that push until they hit a wall.
The specification says they map a force displacement curve. What does that actually mean?
As the robotic ram presses the bearing into the metal casing, it actively measures exactly how much electrical force is required for every single micrometer of downward movement. The computer has a perfect mathematical curve of what a flawless, perfectly straight installation feels like. If the required pressure spikes even slightly above that curve, say, because the bearing is going in just a microscopic fraction of a degree, crooked and catching on the sidewall, the machine doesn't push harder. It physically locks itself up.
It refuses to finish the job.
It stops immediately and flags the part as defective. It stops the microscopic flaw before it ever becomes a part of a moving vehicle.
That is an incredible level of quality control.
Okay, what about the rotor itself? We said earlier that if it vibrates due to imbalance, it will scrape the inside of the motor and seize. How do they ensure a heavy metal cylinder spins perfectly smooth at 12,000 RPM?
They treat it exactly like balancing the tires on your car, but with an obsessive aerospace level of precision. It is called G2.5 dynamic balancing. Every single rotor, 100% of production, goes through an online, two-plane dynamic balancing station.
So they literally spin every single motor up on the factory assembly line before they even finish building it.
Every single one. The robot spins the bare rotor up to high speeds, and highly sensitive accelerometers map the microscopic imbalances in the mass. Because the rotor is a long cylinder, it can be heavy on the left side but light on the right side. That's why it's two-plane balancing. Once it maps the wobble, automated lasers or precision drills physically remove tiny milligram amounts of metal from specific spots or add tiny weights until the rotor hits the ultra-strict G2.5 automotive vibration class. It completely kills the high-frequency vibration at the source. It is amazing how much robotic infrastructure goes into preventing a microscopic wobble, but I have to admit there is one detail in this factory section that completely blew my mind, and I really need you to explain it to me because it sounds absurd. It is about how they screw the high-voltage electrical cables together. The text calls it the smart screwdriver with OCR.
Ah, the torque angle and OCR bolt system. This is my absolute favorite example of how deep automotive process control actually goes. Think about this. When you are bolting massive high-voltage battery cables to the motor inverter, a loose bolt is a literal death sentence for the car.
Right. A loose bolt means there is a microscopic gap between the metal terminals. That poor connection means high electrical resistance. High resistance with hundreds of amps flowing through it causes massive heat, and suddenly your wiring harness melts and catches fire. So obviously they need to make sure the bolt is perfectly tight.
Exactly. So they use a highly advanced two-stage torque angle servo tool. First, it tightens the bolt to a very specific torque setting. Then it relies on an angle measurement, turning the bolt an exact number of degrees further. This guarantees that the seal bolt actually stretches slightly, which acts like a strong spring permanently clamping the metal terminals together. But that isn't the amazing part.
No, the amazing part is what happens before the robotic screwdriver even touches the bolt. The text says it uses OCR optical character recognition cameras.
Right. Before the robot arm picks up the bolt, a high-resolution camera visually scans the threads of every single bolt. It is looking to ensure that the bolt has the exact, precise chemical coating, usually a zinc flake or phosphate coating applied perfectly to its microscopic threads.
I'm having a really hard time wrapping my head around this. You are telling me a camera is scanning the microscopic chemical paint on a screw, and if the paint is wrong, it stops the assembly line. Why does the paint conduct electricity?
No, it has nothing to do with electricity. It has everything to do with the fundamental physics of bolted joints and the coefficient of friction.
Explain that, because to a layperson, tight is just tight.
That is the grand illusion of mechanics. When you use a wrench to tighten a bolt to, say, 50 newton meters of torque, you assume all 50 of those newton meters are going into stretching the bolt and clamping the cables together. In reality, roughly 90% of that rotational force is completely wasted, just overcoming the physical friction of the metal threads rubbing against each other and the underside of the bolt head rubbing against the metal terminal. Only 10% of your effort actually clamps the joint.
Okay, I follow the physics. Friction steals the twisting force.
Exactly. Now, the engineers calculated the perfect clamping force based on the assumption that the bolt has a very specific phosphate chemical coating acting as a microscopic lubricant. If a supplier accidentally ships a batch of bolts that lacks that microscopic layer of phosphate, the metal is dry. The friction coefficient skyrockets.
Oh, I see it now.
If the friction changes, the robotic servo tool will twist the bolt, hit 50 newton meters of resistance, and click off, thinking its job is done. It feels tight. But because the dry friction stole all the force, the bolt never actually stretched. The actual clamping force holding those high-voltage cables together is dangerously low. The connection is loose, the resistance is high, and the car catches fire 3 months later.
That is unbelievable. So if the camera sees the wrong chemical coating, it knows the friction will be wrong, so it rejects the bolt entirely. The machine literally refuses to install it.
Yes. It peels back the curtain on modern manufacturing. It proves that high quality in an EV isn't about telling human workers to work harder or pay closer attention. Humans simply cannot see a missing phosphate coating. True quality is about creating physical and digital systems where making a catastrophic mistake is literally, physically impossible. You engineer the human error entirely out of the process.
So let's take stock of where we are on this journey. We have designed a bulletproof, mathematically perfect blueprint with hardware reflexes. We have built it flawlessly in a robotic factory that checks the chemical friction of individual bolts. Now we have to prove it actually works. We have to take this pristine, perfect machine and try to destroy it.
Welcome to Section 5, DVP&R, Design Verification Plan and Report. This is the crucible. This is where abstract theories meet harsh reality. This is the ultimate torture test.
They literally take these perfectly built, expensive motors into a laboratory and intentionally unleash hell on them to see if the safety systems actually survive.
They have to. You cannot certify an ASIL D component based on computer simulations alone. The specification outlines 3 specific extreme physical validation tests for this A7 fall scenario. Test number 1 is the thermal overload test. In the lab, we just call it the melt test.
What exactly do they do?
They take a brand new motor straight off the assembly line, and they mount it to a test rig. Then they take a massive steel block and solidly bolt the output shaft of the motor to the rig. The motor is physically immobilized. It cannot spin. Then they completely turn off the liquid cooling system. Finally, they command the main inverter to blast the motor with maximum peak DC current for over 5 continuous seconds.
They are trying to intentionally trigger that I2R thermal meltdown we talked about in the very beginning. They want to see if it catches fire.
Exactly. The system's software must realize the motor is locked, recognize the immense uncooled heat building up in the coils, and automatically execute the active open circuit, the freewheeling strategy we discussed for low-speed stalls, to cut the power before the motor destroys itself.
But how do they know the motor actually survived? 5 continuous seconds of maximum amperage with 0 cooling sounds like it would completely cook the internal wiring.
After the 5-second torture test, they let it cool, and then they measure the electrical insulation of the copper stator coils. The insulation is just a microscopically thin layer of polymer resin. They pump 500 volts of high-pressure DC current through the wiring. The insulation resistance must still measure 100 megaohms or higher.
Megaohms, meaning it still perfectly resists the electricity.
Yes. It proves that the polymer insulation did not melt, warp, or degrade even a fraction of a millimeter. Furthermore, they measure the permanent magnets on the rotor. Extreme heat and massive conflicting magnetic fields can permanently demagnetize a magnet. The test proves that the magnet survived the inferno completely unscathed.
It has to survive a literal meltdown scenario without a scratch. Okay, what is test 2?
Test 2 is the bearing EDM and Tyre life test. We can call this the 500-hour earthquake. The goal here is to prove that the invisible EDM lightning and the microscopic mechanical scraping will never happen over the 10 or 15-year lifetime of the vehicle.
How do you simulate a decade of hard driving in a lab?
You compress time by subjecting the motor to extremes. They put the entire motor assembly inside a massive environmental test chamber. They violently swing the ambient temperature from negative 40 degrees Celsius, deep, brittle freeze, all the way up to positive 125 degrees Celsius, which is hotter than boiling water. While it is cycling through these thermal extremes, causing the metal to aggressively expand and contract, they run the silicon carbide inverter at that maximum extreme 10 kilovolts per microsecond switching speed.
They are actively trying to generate the maximum amount of high-frequency electrical noise to force the lightning into the bearings.
Yes, they want to overwhelm the carbon grounding rings. And if baking, freezing, and electrical bombardment wasn't enough, they take the entire running motor assembly and bolt it to a 3-axis electrodynamic vibration table. They shake it violently in all 3 dimensions to simulate the worst possible pothole-ridden road conditions. And they leave it running in this state of absolute chaos for over 500 continuous hours.
500 hours of a freezing, boiling electrical earthquake.
After 500 hours, they pull it out and completely tear the motor down to its individual components. They pull the steel bearings out, slice them open, and put the races under high-powered electron microscopes. The engineers must mathematically prove there are absolutely zero EDM pits and zero microscopic fluting marks. Then they set up laser micrometers and measure the rotor, proving that despite the massive thermal expansion and violent shaking, the TIR wobble is still perfectly under that 0.05 millimeter limit.
That is an incredible standard of evidence. They aren't just trusting the blueprints. They are physically proving that the grounding rings and the robotic balancing actually hold up to reality. But there is a third test mentioned here, and this one involves that 60-millisecond digital brain and the highway speed scenario.
Yes, test 3 is the HEL high-speed injection test. HEL stands for hardware in the loop. This is where they specifically validate the runaway freight train brake, the stepwise active short-circuit logic.
How does hardware in the loop work?
They take the actual physical computer, the real silicon microprocessor brain that will go into the car, and they plug it into a massive, hyper-accurate digital simulation rig. The simulation feeds data to the brain, convincing it that it is actively driving a heavy vehicle down the Autobahn, spinning a motor at a screaming 12,000 RPM under full electrical load.
So the physical computer thinks it is hurtling down the highway.
Right. And then, without any warning, the test engineers inject a malicious zero-speed digital fault signal directly into the processor's data stream. They simulate an instant, violent physical lockup of the motor.
The digital brain thinks the car just hit a brick wall at 70 miles per hour.
Yes. And the stopwatch starts. The brain must react in under 60 milliseconds. It must detect the fault, run the plausibility matrix to verify it isn't a glitch, decide that AOC is too dangerous, and trigger the two-stage stepwise short circuit. The engineers monitor the simulated electrical blowback to ensure the voltage is successfully clamped to 720 volts or less, and that the short circuit current stays safely under 550 amps. It must execute the entire survival protocol without letting a single simulated microchip exceed its thermal limits.
Okay, I have a major question about this. Why do they do this highly critical test in a digital simulation rig? Why use hardware in the loop? We just talked about them physically locking a real motor to a steel table for the melt test. Why not just take a real EV motor, spin it up to 12,000 RPM in the physical lab, and literally jam a metal bar into the gears to see what happens in the real world?
That is a very fair question, and it highlights the extreme forces we're dealing with. The reality is, if you take a high-mass EV motor rotor, spin it to 12,000 RPM, and instantly, physically jam it to zero, you are no longer conducting an engineering test. You are detonating a bomb inside your laboratory.
A bomb, literally.
Literally.
Right.
The rotational kinetic energy stored in that heavy metal mass at 12,000 RPM is astronomical. If you stop it instantly, that energy has to go somewhere. The physical steel drive shaft would instantly shear in half like a twig. The sudden release of energy would cause the rotor to shatter, blasting metal shrapnel completely through the hardened aluminum casing. And simultaneously, the resulting electrical explosion from the uncontrolled generator effect would vaporize the test equipment and potentially kill the engineers standing in the room. It is simply too violent, too dangerous, and too chaotic to safely measure the microsecond electrical reactions we need to validate.
So a physical test at those speeds just destroys the evidence. You'd just be sweeping up dust.
Exactly. You wouldn't learn anything about the software's reaction time because the hardware would disintegrate instantly. That is why the industry relies on hyper-accurate digital twins and HIL fault injection. It allows us to safely validate the microsecond electrical and software responses to a catastrophic mechanical event without risking human lives or destroying multi-million-dollar test labs. It is the only scientifically valid way to prove the 60-millisecond brain actually works under maximum stress.
That context completely changes how I view this. It provides a really satisfying conclusion to this whole journey. It shows that the highly abstract theories we started with, the complex mathematics of field-oriented control, the quantum physics of silicon carbide switching, the precise frictional coefficient of a chemical coating on a bolt, all of it actually survives the harshest physical realities, even if some of those realities have to be simulated because they are simply too violent to exist in a room.
It is a testament to the incredible invisible engineering that surrounds us every day.
Let's do a quick recap of this incredible 5-stage journey, tracing the life cycle of a fatal automotive fault. We started by looking at microscopic plasma sparks acting like lightning inside bearings and heavy rotors scraping the walls by a fraction of a millimeter. We moved into the 60-millisecond digital brain that uses virtual electrical shadows and 2-stage emergency magnetic braking to clamp 720-volt surges. We saw how physical hardware blueprints use analog spinal cord reflexes to bypass the software entirely. We explored an obsessive robotic factory that visually scans the chemical paint on a single bolt before installing it. And finally, we saw how engineers freeze, boil, shake, and mathematically torture these systems to prove that when the worst happens, the car will save your life.
It is a beautiful, highly orchestrated symphony of mechanical, electrical, and software engineering working in perfect unison.
It truly is. But as we wrap up this deep dive, there is one final, really mind-expanding concept tucked away at the very end of the source specification that I want to leave you with because it challenges everything we just talked about regarding physical testing.
Ah, yes. The reference to the Python code simulation.
Exactly. Tucked in the notes, the text mentions that engineers use a Python simulation for transient thermal impedance to precisely calculate what they call the locked rotor time window.
That is the exact split-second time frame they have before the motor reaches catastrophic thermal meltdown during a stall.
Right. They are using pure code lines of Python scripts to mathematically map out the physical melting point of a solid metal engine. And reading that made me wonder, as vehicles become increasingly complex, moving toward fully autonomous driving and even more insane electrical power levels, will these physical torture tests we just talked about eventually become completely obsolete?
It is one of the most fiercely debated topics in the engineering world right now.
Will the future of safety rely entirely on these digital models? Are we moving toward a future where a new car design battles out millions of catastrophic failure simulations in the cloud, refining its own safety algorithms before a single physical piece of metal is ever even cut or bolted together?
The reliance on digital simulation is growing exponentially because, as we saw with the high-speed stall, it allows us to test scenarios that are too dangerous, too complex, or too rare to physically recreate in a lab.
But here's the provocative thought I want you to mull over the next time you get behind the wheel of your car. If we eventually rely entirely on code to predict disaster, can a line of Python code, no matter how infinitely complex, ever truly capture the unpredictable, chaotic, messy reality of mechanical failure on a real-world highway? Can software perfectly predict a rusted bolt, a microscopic flaw in the steel, or a pothole hitting exactly at the wrong angle? Or is there an unpredictable ghost in the physical machine that only a brutal, violent, real-world torture test will ever uncover?
It is an incredibly important question as we hand more and more control of our physical safety over to the digital realm.
It is definitely something to ponder as you cruise at 70 miles per hour, safely surrounded by all that invisible engineering. Thank you for joining us on this deep dive into the microscopic war zone, keeping your EV safe. We will catch you on the next one.